Consider a lone roller staying on the ground. See, this is the ground, and there is a roller in the shape of a circle lying on the ground. Let you are pushing the lone roller from here using a force F. Let F be the applied force. Here you are just pushing the roller, so it will move in this direction. You are staying here and you are applying a force in this direction. So you are just pushing the roller, so it will move in this direction. So there is a force F in this direction, which means you are applying that force. If you consider all the forces acting on this point O, there is a weight W equal to mg acting vertically downward, which is the weight of the roller. Let's draw a horizontal and a vertical line. And if you resolve the force into two perpendicular components, there is a, let's call this angle be theta, then this will be f cos theta, and there is a perpendicular component f sin theta. And you know the reaction of the roller will be in this direction, R. So these are the different forces acting on the roller, where F is the push, the force with which you push the roller. So considering the vertical equilibrium of the body, the net upward force will be numerically equal to net downward force. So the upward force acting on the roller is R, but there are two downward forces. One is weight mg plus an f sin theta. Clear? So since the roller is moving in this direction towards right, there is a friction acting towards the left or in the opposite direction of motion. Let's call that as kinetic friction Fk. But you know the kinetic friction is always the coefficient of kinetic friction times the normal reaction. But you know this one is the normal reaction. So Fk is equal to mu k times mg plus f sin theta. Let's call that as equation number 1. So what's the case when you are pulling the roller? That means if you are applying a force from here, it's like when you tie a rope in the end of the roller and you just place it on your shoulder like this. You just put that on your shoulder and try to pull that in this direction. So roller moves in this direction, definitely. So the forces acting in here are, there is a force of pull F in this direction. Let's draw the horizontal and vertical lines. Okay, let this angle be theta. Then this force can be resolved into an f sin theta in the vertical direction and an f cos theta in the horizontal direction. Definitely, the weight acting on the roller or the weight of the roller is in this direction, mg. And reaction is always in the direction, that is in this direction, opposite to weight. So here, if you consider the equilibrium of the roller or the vertical equilibrium of the roller, we have net upward force is equal to net downward force. So what are the net upward force? That is a R reaction plus an F sin theta equal to net downward force is equal to mg. So let's call this as R prime because we previously considered that as R. So here it is R prime. Therefore, R prime is equal to mg minus f sine theta. Let's call that as equation number 1. And you know the friction acts always in a direction opposite to the motion of the body. So this is the kinetic friction acting in here. Let's call that as Fk prime. So Fk prime will be mu k times the reaction. So Fk prime is equal to mu k times R prime is equal to mg minus f sine theta. Clear? Let's call that as equation number 1. Before we got, in the case of push, we have friction Fk is equal to mu k times mg plus f sine theta. Clearly, if you look into these two equations, that is Fk and Fk prime, you understand that Fk is greater than Fk prime. Since here it is negative, for here it is minus, here it is positive, so obviously this one is greater. So friction is greater in the case when you push the roller. So it is difficult to push than to pull a roller. Clear?